In this video, I'll be showing you how to use the Runge Kutta fourth order to solve for an ordinary differential equation given an initial value problem. And so before we start, I recommend that you either copy this table down here, just so that it becomes easier along the video if you want to input values, or you can also download this Excel file, which I've shared in the description below. And so the Excel file contains all the complete workings already. But again, if you want to understand how we got those values, I recommend that you follow through with this video. Right. Before moving forward, I think it's much easier to understand what we're doing here with the Runge Kutta method through this illustration. And so basically, let's just say, for example, we have this person who's trying to climb up a mountain. And we know that at the base of the mountain, or x equals 0, that person is at a height of 1. Now what we want to figure out is that at the peak of the mountain, or x equals 2, what height that person is at. And so we can use the Runge Kutta method to model this or predict this. Right, so here we're given our problem, which is the ODE. And we have our RK-4 formula, which looks quite long, but trust me, it's actually very simple. So it's comprised of various components, K1, 2, 3, and 4. And the reason it is because we have to find these components first before we can use the actual formula. And it's quite systematic, so we have to find K1 first, and then we can find K2, as we need K1 to find K2, and we need K2 to find K3, and we need K3 to find K4. But it's trust me, it's actually very simple. And we have our parameters here, which are the initial values of x0 and y1. And we have our step size of subsize h of 0.1, meaning if we look at it through our illustration, the step size is simply the distance covered per step. So if this person climbs a mountain, the person's climbing it per 0.1 steps, so 0.1, 0.1, 0.1, until that person reaches x equals 2. And we have our range from 0 to 2, which is simply from the base of the mountain, 0, up to the peak of the mountain 2. And with that, let's move on to our iteration table. And here we want to reference our initial values, which xi at 0 is simply 0, and yi at 0 is simply 1. And k1 here is the following: f of xi minus f of xi yi, which simply is the evaluation of this function using the xi and yi values. So it's simply just x squared plus y, like this. And what we're doing here is basically replacing the x and y values with our x and y values. And here we have xi plus 1/2 h, which is simply just xi plus 1/2 times h. Here, our step size, $sign that since it's constant. And here we have yi plus 1/2 h as well. 1/2 times k1 times h. But don't forget to $sign the h here. Okay. And we have k2, where k2 we know to be the evaluation of this function here with xi plus 1/2 h and yi plus 1/2 k1h, which again is simply just replacing the x's and y's here with these x and y's here. So it's simply just this squared plus this. And we have yi plus 1/2 k2h, which is simply just yi plus 1/2 times k2, which we know from here, multiplied with h, the step size. And don't forget to $sign that too. And k3 is simply the evaluation of this function again, but with our new x and y values. So with xi plus 1/2 h and yi plus 1/2 k2h. So it's simply just xi plus 1/2 h, take this one here, squared, plus y, right? And y in this case is this y, the yi plus 1/2 k2h here. Again, if you forgot, we're simply just changing the x and y's here with our new x and y's. And here we have xi plus h, so we take xi from the start, plus our step size h, $sign that, and we have yi plus k3h. So take yi here, plus k3, which we got here, plus h. and $the h. And lastly, K4 is simply just the evaluation again of this function, but with our new x and y values. So it's with xi plus h and y plus k3h. So it's simply this squared plus this. Okay, now let's move on to the second row. Now to find the second xi value, it's simply just the initial xi value plus our step size, $, and our yi now is where we implement the Runge-Kutta formula. So to find the new yi, it's simply just the previous yi, which I'm highlighting right now, but it's being blocked by the cell. But again, just take our previous yi plus 1/6 times h, so h is our step size, times k1 plus 2k2 plus 2k3 plus k4. So k1 here, let's take k1, whoops, okay, so k1 here, plus 2 times k2 here, plus 2 times k3 here, and plus k4. Again, this is being blocked by the cells above, but again, just copy the formula here. All right, so we've done that, and now we can just copy the remaining cells down like this. So highlight this and Control D, or just drag with your mouse, and we're basically done. So highlight all of this and Control D. And there you go. We finished iterating with the Runge-Kutta formula. And so we find out that at, wait, let's just make this tidy. Okay, so we find out that at x equals 2, the person is at a height of 12.16, let's say in this case, meters. So initially at the base of the mountain, the person is at a height of 1. Now at the peak of the mountain, or x equals 2, the person is at a height of 12.16 meters. So that is it for the Runge-Kutta method. I think it's a fairly straightforward method that's quite easy to use, despite having a long formula. I also have some other videos on other numerical methods, such as the Runge-Kutta second order, the Adam-Bashford, Euler, fixed point, false position, Newton-Raphson, and so on. So if you're interested, please check those out as well. Right, thank you for watching.